is the average rainfall for a 3-hour duration storm is 2.7 centimeters and the loss rate is 0.3 centimeters per hour. The flood hydrograph has a base flow of 20 cubic meters per second, produces a peak flow of 210 cubic meters per second. The peak of 3-hour unit hydrograph is, we have to find out the peak of 3-hour unit hydrograph. So average rainfall is given as 2.7 centimeters and the loss rate is 0.3 centimeters per hour. This is for 3-hour duration, so 0.9 centimeters is the loss. So the remaining is 1.8 centimeters is the average rainfall. From the unit hydrograph concept, for a 1.8 centimeter rainfall, average rainfall, the peak flow is 210 minus 20, that is 190 cubic meters per second for 1 centimeters is an unit hydrograph. That is, the question mark we will get is equal to 100, that is 190 into 1 by 1.8, that is 105.5 cubic meters per second. This is peak at 3-hour unit hydrograph. So 105.5 cubic meters per second, option B is correct. We have to match list 1 with the list 2. So the list 1 is given as Gutta Parcha, Carborundum and Breeze. Here in list 2 it is given as Indian rubber, furnace ashes and waste from furnaces mixing sand and carborundum, carbon. So Gutta Parcha is nothing but Indian rubber. Carborundum is nothing but mixing of sand with carbon. Breeze, furnace ashes. So P1, Q4, R2. Option A is correct. In case of riveted connection, the following terms are mentioned. So we have to choose the appropriate answer for these conditions. The conditions were, one is the shearing strength of the rivets, the bearing strength of the rivets on the riveted material, the tensile strength of the riveted part at the weakest section. Which of the following is correct in case of strength of rivet connections? When calculating strength of rivet connections, what we are going to calculate the say shear strength, bearing strength and tensile strength of the riveted part at weakest section. The three we will find out, 1, 2, 3, we will find out the three strengths and we are going to take as a rivet is going to be the smallest of these three conditions. Lesser good thing we are going to take and we are going to design the rivets. So here the smaller of the above three conditions is going to be the appropriate answer. So option A is correct. Here the question is, the normal velocity of flow in a river is 1.5 meters per second is given. The normal waterway under the bridge, the artificial waterway under the bridge and enlarged upstream area of the bridge are given as 8,700, 10,000 respectively. We have to calculate the increase in velocity due to upflux. So by using Merriman's formula. So if you know the equation or Merriman's formula, then you can easily calculate the increase in velocity due to the upflux. So the Merriman's formula giving that HA, causing flow or flux due to a flux, is V square by 2Z into A by C A whole square minus A by A1. We will describe the each term over here. This is velocity of flow, where A is the waterway under the bridge, A1 is the upstream area of the bridge, and small a is the artificial waterway of the bridge. So By substituting these values in the equation 1, we will get V is 1.5 square to 9.81. A is 8000. That is the normal waterway under the bridge. C is 0.98 and small a is the waterway enlarged upstream area. Now artificial waterway is how much? 7000, right? Whole square minus 8000 divided by 10,000. This is upstream area CA1 is equal to, we will get the value approximately 0.0642 meters. So what we have to calculate? Increase in velocity is due to of flux. VA, increase in velocity due to of flux is root 2G HA. Root 2 into 9.81, HA is 0.0642 meters. That implies 1.122 meters per second. 1.122 meters per second is option B is correct. For our unit hydrograph of catchment of triangle in shape with a base of, if you represent the question in terms of the diagram, we will get a 8-hour hydrograph, the base of a triangle. The area of catchment is given as 720 kilometers square, and it is a 4-hour unit hydrograph, that is 1 centimeters in 4 hours. What is the peak discharge? We have to calculate this QP, peak discharge. We will represent it as QP. So QP we have to calculate. That implies, by using a unit hydrograph concept, we came to know that the area of triangle of base into height QP, because the options are in terms of seconds, so 3600 seconds divided by 720 will convert in terms of kilometer square into meters, that is 10 to the power of 6 into 100 is equal to 1 centimeter. Therefore QP is equal to 50 cubic meters per second. So option C is correct. How many milligrams per liter each of ferrous iron can be oxidized by 1 milligram per liter of potassium permanganate? For this, we have to know the chemical reaction between the potassium permanganate and ferrous iron. So for ferrous iron is Fe plus 2. We know the equation, that is 3Fe plus 2 plus 4H plus KMnO4 gives rise to MnO4 O2 plus 2Fe plus 3 plus K plus 2H2O. So for this molecular weight, 3 into 55.85, we know 39.1 plus 54.94 plus 4 into 16. This is for KMnO4 molecular weight. This is for Fe plus 2 ion molecular weight. So what we have to find out for 1 milligrams per liter of potassium permanganate. This is 1 milligrams per liter. What is this value? We have to calculate by proportion rule. This question mark is equal to 3 into 55.85 divided by 159. That is equal to 1.06 milligrams per liter of ferrous iron is theoretically required. That is 1.06. Option A is correct.